Science Guy. Bill Nye, the Science Guy. Bill Nye, the Science Guy.
Science rules.
Bill Nye, the Science Guy.
Inertia is a property of matter.
Bill Nye, the Science Guy.
T minus 7 seconds.
Bill Nye, the Science Guy.
Brought to you by Echo. Bouncing sound waves anytime you call.
You and I see, hear, and think with waves. See, because energy travels in waves, like light travels in waves. Sound travels in waves. The television picture you're watching right now started out as a wave. Take a look at this. It's our metal rod wave machine of science. Now, when I move the rod at this end up and down, watch what happens. It makes a wave that moves side to side. It even bounces off this end and comes back. Now, a wave like this can carry energy. So watch. I can knock this ball off of here at this end by making a wave at this end. See that? Now, different forms of energy move in different ways. For example, when you make sound energy with a guitar, you pluck the string. And that sets up a wave in the string. And the wave in the string sets up waves in the air that we hear as sound. But also, it sets up a wave on the screen that's connected to a microphone. See? And look, there's a wave in this speaker. Now, the wave in the speaker, the wave on the screen, the wave in the air, and the wave in the string are all different forms of the same energy. They're all waves. Oh, yeah.
Coming next week to the BNSG Network. It's Wave Week. Nothing but waves all week long. Big waves, little waves, 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 waves. Going up and down and back and forth all week long on Wave.
If waves all look alike, how can we tell them apart? Well, please consider the following. If waves are nice and even like these, we can't really tell them apart unless we stand in one place. This is our observer kid on a stick.
Hi, Bill.
And where she is, she can see the top of one wave. Then as the waves go by, she can see the top of the next wave. Now the distance from here to here, the length, is called the wavelength. That's what we call it, the wavelength. Now there's another thing about waves that you can observe, and it's called the frequency. If you go to the library often, we say you frequent the library. That's how often you go there. So waves like this are coming by often, and we say they have a high frequency. If I slow it down, the waves coming by have a low frequency. Now you know about high and low frequency waves because you know about high and low frequency sounds. Take a look at this. This is an oscilloscope. It lets us see waves. So watch. If I make a high frequency sound,
1,000 hertz at reference fluxivity of 250 nanowevers per meter.
You can see that the waves are close together and the wavelength is short.
Equalization per NAB standard.
But if I make a low frequency sound,
Full track recording with no compensation for multi-track reproduction.
the waves are farther apart. They have a longer wavelength, and we say they have a lower frequency. So high frequency waves have the waves close together. Ha! And low frequency waves have the waves far apart. See? Thank you for joining me on Consider the following.
The wavelength depends on how fast the waves are made. The faster I vibrate the spring, the shorter the wavelength will be. As I increase the frequency of the waves, that is, make more waves per second, the shorter the wavelength becomes.
Waves can move in all directions. Check it out. Set up some dominoes like the spokes of a wheel and leave enough room in the middle that a tennis ball can almost fit. Then drop the tennis ball in the middle. Cool. See how all the dominoes fell, even though only the dominoes near the center were hit by the ball? Waves kind of work the same way. Energy travels through the wave out in all directions. You think I'm lying? Try it.
When we have a wave like this one, we can measure its frequency by counting the peaks. We can measure its wavelength by measuring the distance from here to here. But there's one more thing we can measure. That's the amplitude. You've probably heard the word amplifier. An amplifier has a volume knob that controls the amplitude, how big the sound waves are. So, we can count peaks to get the frequency. We can measure this distance to get the wavelength, or we can measure this distance to get the amplitude.
Honey, what do you think of my nails? I just had them done.
Yeah, honey, they're great.
What do you think about my hair? You like my hair? I just had my hair done. Do you like the hair?
Yeah, honey, I like it a lot.
You don't pay attention to me anymore. What's wrong with me? Don't you love me anymore?
The bridge. Honey, I need a quarter for the bridge.
Reggie, give Mother a quarter. Here's your quarter.
Thank you.
Now I'm going to show you a couple of more things that all waves have in common.
All waves have a similar shape.
Energy moves in waves.
This motor and these 3 points are making waves in this tank of water. The waves are running into each other. And when waves run into each other, they make patterns. That's the way waves work. Take a look at this. This slide has many, many fine grooves cut in it. And when the light passes through the grooves, it breaks up into a pattern we call the rainbow. We see different wavelengths as different colors. Now, because light breaks up into patterns like this, scientists like to think of light as traveling in waves. The wavelengths of light are measured in billionths of a meter. And they're what we call electromagnetic waves. Electromagnetic waves. Now, you know a lot of electromagnetic waves. There's light, and X-rays, and microwaves, like in a microwave oven, radar, and radio and television signals also travel in waves. Now, the wavelength of a television signal, like the one you're watching right now, might be a few meters, like the distance from me to the camera. So the only difference between these waves and these waves is the wavelength. See? They're all electromagnetic waves.
This is KC7VOJ.
KC7VOJ, this is Alpha 6 Uniform. My name is Scott, and I am in Riverside, California.
This is our antenna for our radio, and when we're talking on it, the waves leave the antenna and go thousands of miles away.
When you send a wave from a ham radio, it goes into an antenna tower and it goes off from the antenna 70 miles up in the air and bounces on the atmosphere and then comes back down in a totally different part of the world.
I've gotten to California, Idaho, and Nevada.
Then if you're lucky, it'll go back up again, and bounce again, and you might land somewhere really far, and you could get a contact.
You need to use the waves. You can't see them, but they're there.
By the way, how is everything up there in the Seattle area today? Is it nice or is it rainy?
You can talk to all sorts of people around the world in maybe different states.
Well, right now, with radio waves, there's definitely a very good radio wave path between Southern California and the Seattle area because you're coming in very, very strong.
That's another bit of evidence indicating that radio signals are waves.
This is an X-ray machine. It makes X-ray waves. Now, X-ray waves are just like light waves, only they're much closer together. They have much higher frequency. They have much higher energy. X-rays have so much energy they can go right through your skin and muscle till they hit your bones. And then look, you can see them. Now, this machine uses a very small amount of X-rays, very low dosage, so we can see my bones. See? Look, you can do this too. Look. Arf, arf, arf. It's a dog. See?
What you see is called a train of waves. The distance between here and here is called one wavelength. A wavelength is the distance between two successive parts that are alike.
Having fun in the waves!
Fed up with unreliable carpet cleaners? Tired of rubbing and scrubbing? Then try new improved Wave from the Breaker Group. Wave comes directly to your door and washes everything in, on, or around your house. Wave is all natural and is carefully crafted on the high seas by wind and its thermohaline co-workers. Wave is absolutely free and never stops. Try new improved Wave today.
Earthquakes can travel in waves. Yeah, sometimes an earthquake over here in North America can be felt all the way over here in Africa. That's because they're waves, some of them going right through the earth and some of them going along the earth's surface that carry the energy of the earthquake from here all the way over to here. Take a look at this. It's our plastic Earth surface wave model of science. And this blue pad represents the Earth's surface. Now, the surface of the Earth is floating on molten liquid rock, but here it's floating on liquid water. So watch what happens when we make a wave over here. It can go from here all the way over there. Watch. And look, the wave in the pad, in the surface of the Earth, can make this building fall right over. Of course, it's not really a building, it's a model of wooden blocks.
Understood, yeah.
But anyway, earthquake waves are called seismic waves. Seismic waves. So they're waves that move through a whole planet.
This week on Wave Week, watch out for Wave Woman. Able to hail a speeding taxi with a single hand. Able to greet friends and neighbors with a flick of her wrist. She's a freak for frequency.
This is a wave tank. Scientists use this to measure waves in water. Now, if you look closely, you can see the wavelength. It's the distance from the top of one wave to the top of the next wave. Or you can measure it from the bottom of one wave to the bottom of the next wave. It's the same distance. And then if you stand in one place and count, you can measure the frequency.
1, 2, 3, 4, 5, 6, 7. Bill?
It's about 2 waves every second.
Oh.
And then this is the amplitude, the height of the wave. Take a look at these particles here in the middle. So they're moving around in little circles, but they're not moving that way along with the waves. The waves are going right through the water without carrying much water with them. Isn't that cool? That's just the way it is with waves.
This plane is designed to fly through the speed of sound. As a matter of fact, over twice the speed of sound. As an airplane moves through the air normally moves smoothly around the nose of an airplane staying close to the fuselage. But as we go supersonic, the air molecules in front of the nose cannot move out of the way quick enough, and they form a tremendous wave of energy emanating from the sides of the nose. This tremendous wave of energy coming off the nose of the airplane is much like the wave that comes off a boat going through the water. Matter of fact, this wave is so powerful that if we were close enough to it, we would hear it in the form of a loud sonic boom.
Oh, hi. Musical instruments make sound waves. Now, the longer the whistle, the longer the wave. And the lower the note. Pipe organs work the same way. High note, short pipe, short wave. Low note, long pipe, long wave. Different length tubes make different length sound waves, and it makes different pitches of sound. Say, Mel, can you play something funky?
Now, what do waves do? Well, first of all, they travel. They go places. They move. When the waves reach the rowboat, they make it move. So it appears that waves can carry energy from one place to another.
Waves don't always move like this. Now, sometimes they move like this. They squeeze together and spread apart. That's how waves go through something like this spring. Watch. I'll squeeze this end and let go. See, there's a wave going through the spring just by squeezing and spreading. There's no motion up and down. It's the same way sound waves travel through the air. Air molecules bump into each other, so some places they're close together, and other places they're spread far apart. The air molecules are moving kind of like these pool balls.
Midnight Soda Bill needs this shot. Oh! 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 Oh!
It's kind of like that. Kind of like the pool balls, not exactly. As I was saying, sound waves can travel through the air the same way waves can travel through billiard balls. Okay, here we go. Here we go.
Midnight Soda tries it again. He's got it!
There, see, it worked. That's because the billiard balls were close together. Now, the molecules in air, well, they're very close together, so sound travels great.
Now, watch what happens in slow motion when I vibrate the spring just once. The movement travels down the spring, and when it reaches the other end, it bounces back. It's reflected.
Sonar uses sound waves to find things underwater. Sonar equipment sends out sound waves in a sharp pulse, kind of a ping, and then we wait for the waves to come back. Pong. See, it's kind of like ping pong underwater. It works something like this. Sonar uses sound waves to tell how far away things are. If you have enough waves close enough together, you can generate an image. Kind of like when we press this guy into this bed of pins. See the image? That would be kind of like sonar. Now, submarines and mammals that live in the water and fishing boats use sonar to find things and find how far away things are in the water. See, it's saying submarines, sonar, so good.
Listen up. When I yell, the sound waves leave my mouth and hit that hard surface over there. Then they come back to me. Waves! Waves! waves keep their shape even though they bounced.
Echoes! 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 Echoes!
Cool, yeah?
Science!
What?
Ooh, energy moves in waves. Wavelengths grow so long before my eyes. Look like curves drawn on a page. Amplitude describes a wave's height, like a tower in the city. But don't, oh no, forget shape, 'cause all waves have the same. Yeah, 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 yeah. Ooh, energy moves in waves every day. Yeah, yeah. Whether sound waves or gamma rays, that's its way. Yeah, yeah. Ultraviolet and microwaves. Visible light are light waves you can see, see, see. They've got a quick frequency. But don't, oh no, no, forget shape, la-di-da, 'cause all waves have the same. Yeah, yeah.
Well, that's our show. Thanks for watching. If you'll excuse me, I've got some subsurface harmonics to monitor. See ya!
Produced in association with the National Science Foundation.
What was he saying?
Lower the amplitude for you. Science! 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 Hey, how about that? Hey, Jim, how about this? Okay, ready? Science rules. I mean, science.
See accompanying instructions for using this test tape.
It's a wave. Oh, okay. Yeah, I get you. It's a wave. I mean, it's a wave. Sorry about my voice. I don't know what's going on.
Woo! Woo! Beautiful day for the Doppler effect. Woo!